Hello, everybody. I was honored again to be a chairman of this session number 13. We've got 4 contributions, and the first speaker is Joško Poč from Slovak Academy of Science Mathematical Institute. And I cannot see the title, but he will explain and introduce.
Thank you for the introduction. As you can see, this is a joint work of 4 authors, and it deals with some relatively new kind of averaging operators. Let me start. Probably, as you all know, there are well-known Pythagorean means. There are 3 types of these means, and the first one is the arithmetic mean, which is defined in this way, as you know. The other one is the geometric mean, and the third one is the harmonic mean, which is defined in this way. As you can see, here is some nice graphical interpretation of these means, and as you can see directly from this picture, there is well-known AG inequality, which is known in this way. So these are probably the best-known means or averages which are used. Another type of means are the so-called weighted means, and they are defined using some vector which have n indexes in the sum which are equal to 1. And the weighted arithmetic mean is defined in this way, that each input x is weighted by the appropriate weight, and the corresponding result is the sum of these products. Another type of arithmetic mean is the so-called ordered weighted arithmetic mean, and here some ordering of the inputs come into play, and we have some permutation, and we order the inputs according to the standard ordering of real numbers, and the result is computed in this way, that the first weight is applied to the greatest value, and so on. So this is the well-known ordered weighted arithmetic mean. Recently, Medina and Jaeger introduced the so-called ordered functional weighted averaging operators, and the major novelty was that instead of constant vector of weights, they consider functional weights. That it is that each weight particular is a function, NRE function from unit cube to the interval 0, 1. And again, we have this norm that the sum of each weights is equal to 1, and the corresponding ordered functional weighted operator is defined in such a way that classical ordered weighting operator, that we have permutation which order the inputs, and to the greatest input there is applied the first weight, to the second one the second, and so on. So this is the standard definition of these operators. What is important, that similarly as in the case of OVA operators, this definition is independent with the choice of permutation. Yes, we can have several permutations with the corresponding ordering, but this does not affect the result. So this is well defined. Okay, what is the key property of this functional operators, and it is that all these operators are below maximum and upper of the minimum functions. Yeah, they are in. They can be considered as the so-called means, and this definition of means, as I know, goes back to Cauchy, who introduces mean as precisely as a function between minimum and maximum. These functions are called as intermediate functions. What is important that any intermediate function, that is the function between minimum and maximum, can be representing as OFWA operator, and this representation is given with this simple formula, which involves only one function. Is C? C. So any intermediate function can be represented as this kind of operator, and instead of n independent functions, we use only one. So, and in this case, we obtain this representation of each intermediate function. And as you can see, if we consider the unit cube without the, we can say, diagonal, then this weighting function is uniquely determined with this formula. Yes, this is not so difficult to show. And as what was our main, that this representation established a mapping from the space of all functions which are defined on the 0, 1 cube to the class of all intermediate functions which are defined on this 0, 1 cube. And this mapping is given by, given a function phi, there is assigned this kind of operator. And what was our main? It was the investigate algebraical and topological properties of this method. Yeah, we have some representation, and the aim was to investigate some of its properties. So, considering algebraic properties, if the psi function can be arbitrary, but if we consider the monotone function, then it can be shown that the resulting OFWA operator is again a monotone. So if we restrict this representation function to the class of aggregation functions, we obtain monotone idempotent intermediate functions which coincide with the class of idempotent n-ary functions. Yeah. So this restricted mapping goes from aggregation functions to the idempotent aggregation functions defined on 0, 1. So again, here is the explanation of these symbols. It can be shown that, however, if we restrict to the monotone functions, then this assignment is not surjective, neither injective. Yeah, you can find some idempotent functions which are not in the range of this operator. So it has not so nice property as if we are in the whole class of functions. So what are the algebraic properties of the class of all functions? It is not closed under addition or multiplication. So generally it has not the structure of vector space. So we mainly consider its lattice structure, and it is well known that this class of all these functions forms a complete lattice with respect to the pointwise operations of suprema and infima. So it can be shown that this correspondence, this mapping, is in fact a lattice homomorphism. That means that it presents finite suprema and infima. And also it can be shown that if we have this finite homomorphism, then we can look at the congruence relations, and it can be shown that the corresponding congruence relation is the so-called complete. And this is equivalent to the fact that if we look at the preimage of some single functions, then the resulting preimage of these functions is equal to the closed interval functions. Okay? And if this holds, then in this case, this congruence is complete. And what is known that complete congruences corresponds to the complete homomorphisms. So this mapping is in fact a complete homomorphism, which is maybe a little bit surprising because this representation involves standard arithmetic operations, and it also preserves the suprema, and so this is one of the results concerning algebraic. As yeah, you can see that here are operation of maximum, minimum, but the standard operation of multiplication and addition. So here are some results concerning addition and multiplication. So this this operator is positively homogeneous if and only if this corresponding function c is constant on this set Hn and is constant under multiplication. This means that c of c times a is equal to the ca. And also it is shift invariant if and only if c is constant with respect to this shift. So these are some properties related to algebraic structure of these functions. Okay, so we shift to the topological properties. If we consider the set of all functions defined on the cube and intermediate functions defined on the cube, these are naturally subsets of the normed space of all bounded real functions, which are defined on the set 0, 1 to the n. So this norm, as you know, is given as a supremum of all function values from where a is from the given domain. So this is the well-known norm, and according to this norm, this spaces forms a metric space. The norm, the metric is given by as a difference of the two norm of difference of these two functions. It is given as a supremum of all these absolute values. So what is the first property? If we consider this mapping from the class of all functions to the class of all intermediate functions, it is Lipschitz continuous. And as you know, if it is Lipschitz continuous, then it is automatically uniformly continuous. So with respect to this norm, here is some simple computation. If we take two values of this operator, then we obtain that it equals to this sum, and with the standard property of absolute value, we obtain this formula. And as you know, we are on the interval 0, 1, so this maximum is smaller than 1. Also, this minimum is smaller than 1, so we can obtain this estimation. So finally, difference of these values is smaller than 2 times of the norm of these two functions. So this means that this function is 2 Lipschitz continuous. So this is the first property. And we can ask where, under which conditions result is continuous. So if we have f as a result of this, it is an OAF operator, and it is representing by one single function, then it is continuous if and only if the corresponding function is continuous on this set Hn. It means the whole cube without diagonal. Yeah. So in this case, this function is given by this formula. And you can see that if this is continuous, then also this fraction is also continuous. So we have that phi is continuous on this subset provided f is continuous. Conversely, it can be seen that if psi is continuous on this set, then also the resulting function is continuous. So we have nice condition. So this we can consider mapping from the continuous functions defined on the interval 0, 1 to the class of all continuous intermediate functions. And this mapping is denoted by S. This C with C, and this function is continuous, yeah, because the whole mapping is continuous. So it can be shown that this mapping is injective because the corresponding function is uniquely determined on the dense subset. However, this mapping is not surjective. Yeah? We can find some functions which is not the preimage, which has not continuous preimage. It has a preimage, but it is not continuous. So this is not so good property. So what can be said about the range of the mapping? And one of the good property is that if we consider the range of the of this mapping of all continuous functions, then this set is dense in the class of all intermediate functions. And the key tool to prove this theorem was the so-called Titze extension theorem, which roughly says that any continuous functions from a closed subset of a normal space can be extended to the whole space. Yeah, this is a folklore result in the general topology. So, and consequently, given epsilon and given any continuous function, intermediate continuous function, we were able to find of continuous of FA operator, which was the image of some continuous functions defined on this interval, such the resulting norm was smaller than given epsilon. And this shows that the range is dense. And as a last slide, the possible application of these results is that it enables us to identify some dense subsets of intermediate functions. Yeah. First, since this mapping is a complete lattice homomorphism, we were able to find some join or meet dense subsets in the lattice of all functions from the algebraical point of view. Another possibility is, since this operator has dense range in this set of continuous intermediate functions, it can be used to find some uniform approximation. So, for example, one can apply Stone-Weierstrass theorem to find dense subsets in the domain, and then transform it to the class of intermediate functions. Yeah, so this is all still on work. So this is only some possible application of. So okay, thank you for your.
Thank you for nice results going deeper into the structure of FW, and we've got operators, and we've got maybe time for one short or two short questions. Are there any? Everything is clear. Maybe I will ask. This is a standard thing that the standard of an operator can be embedded or to be a special part of Schoke integral with respect to symmetric measure. Is there any possibility to extend this OFWA into some integral with respect to some measure?
I don't know exactly because it covers all intermediate functions. So if shocked integral is able to cover all intermediate functions, then
maybe other kind of integrals.
maybe yes, but as a standard shocked integral, it is not possible. But maybe as some integral as we've seen in the previous lecture, there will be maybe possibility.
Okay. Are there any further comments or questions, remarks? If not, thanks the speaker again. And we will continue with two contributions from Umberto's team. The first one will be presented by Miquel Ferrero Jaurieta, and the title is on the screen, so the stage is yours.
Okay. Okay. Hello, everyone. I am Miquel Ferrero Jorrieta from the Public University of Navarre. This work is done in collaboration with Lucas, Denko, and Umberto, and is part of work that I did in my last stay in STU in Bratislava about some ideas about extending I/O operators into the multivariate domain. Okay, when we are designing information aggregation or fusion techniques, common strategies to take the importance somehow of each part of each piece of information that we are going to fuse. Based on any criteria that we are considering, we can order this information according to some importance. Some examples in order to rank, in order to order this information are very common O operators, where the information, the inputs are ordered based on the absolute magnitudes, or induced O operators, where the values are ordered with taking into account an auxiliary or a secondary vector. There are many other operators, but I am going to center in these I/O or induced O operators. Also, frequently the information is compressed about several attributes, coordinates, etc. No, frequently information is multi-valued, and in order to order this information, we have an additional problem because we cannot order vectors or multi-valued information based on partial orders. Normally, in order to establish an order on an n-dimensional space, we try to move to one-dimensional space to some suitable unidimensional space in order to order. In the field of the aggregation functions theory, there have been several approaches in order to have a multivariate order. Some of them are the admissible orders, the admissible permutations, degree of totalness, etc. In this work, I'm going to present two small approaches to extend the I/O operators on admissible orders and based on all the admissible permutations. We are going to propose also a reformulation of the I/O operator, providing a new definition, a new, more flexible definition. And finally, we are going to apply this extension into in order to aggregate multi-valued time series predictions, where the model predictions and their associated metrics are multi-valued, are vector valued. Okay, first I'm going to give some order preliminaries. We are going to take into account the following partial order, and an admissible order is taking into account a poset. It has to satisfy two conditions. One is that it's total, and the other one is that for each couple of values, if this couple of values are ordered with a partial order, there has to be also ordered by an admissible one. And also another thing is that we can construct admissible orders by means of sequences of aggregation functions. Later in the application, we are going to use, or we are going to construct better, admissible orders by means of sequences of aggregation functions. So there can be many admissible orders. So in order to take into account all the possible arrangements of some set of vectors, the concept of admissible permutation was introduced. In this sense, the admissible permutations with respect to a set of vectors and with respect to the partial order, it has to satisfy the to be current with the partial order, and if there are two elements that they are equal, we will obtain an interval in natural numbers. Also a notation for the set of all admissible permutations, and also we have to take into account that the concept of admissible permutation was given in the context of Schottky integral, where we are interested in decreasing permutations and or increasing permutations. And as we are going to talk about our operators in this context, we are going to use the concept of reverse permutation, which is only to sweep the values of the permutation. Okay. Now I'm going to present the classical I/O operator, changing a bit the notation in order to be current also with the contribution. Is the classical Jagger I/O operator. We are going to take into account the set of all normalized weighting vectors. Sorry, and take into account a weighting vector and set which is the inducing values. The I/O operator is defined in the following way, where the values that are aggregating are the x1s, and they are ordering according to set values. In order, as I asked you before, in order to be a bit more flexible, we have we have generalized this operator. We have reformulated this operator with a increasing symmetric and idempotent extended function. In this way, we present the following mapping with this, which is an I/O operator, and as in the previous cases, the values that are aggregating are the x1s. Here we take into account all the reverse permutations, take into account the set of all admissible permutations of A, and also, as I'm going to tell you before later, in this case, as the values that we are aggregating and also the inducing values are univalued, the set of admissible permutations of A is only the one that takes into account the ties of the values. Okay. Okay, taking this reformulated operator, we present the vector O operator, where we take into account the natural number or a vector of a weighting vector, and also an H, which is a set valued mapping. No, take into account that this set valued mapping of this set is subset of or equal to the set of all admissible permutations, and also the M, which was the increasing symmetric and idempotent extended extension. In this way, the BioWA or the vector induced OA with respect to this triplet is the following mapping. And as in the previous case, we take into account these values and this set of admissible permutations. Taking into account this definition, we can talk about some particular cases. If the input and the inducing values are scalar, we recover the reformulated I/O operator. Also, if moreover the set is the set of all admissible permutations, and the function, not the aggregation function, is the arithmetic mean, we recover the IOI in sense of this reference. Also, the inducing values and the input values, we recover the classical O operator. If the input is multi-valued and the inducing value is scalar, only we can obtain multiple admissible permutations if we satisfy the following conditions. And now, as I have said you before, I'm going to present two special cases depending on the set admissible permutations HA, which we are going to base on the same definition. The first case is going to be the vector-induced operator with respect to the admissible order. We take into account and a fixed admissible order. And in this case, as I had with you before, as the admissible order is a total order, the permutations of this set only differs in the ties of the inducing vectors. And also note that if these vectors, the inducing values and the inputs are equal, we recover the n-dimensional operator given in this reference by De Miguel et al. Also, the second case is the Iowa with respect to all the admissible permutations. We take into account a standard partial order, and this set will be the set of all admissible permutations. So also, if we are working with a bounded convex poset of a vector lattice, and we satisfy also these restrictions, we recover the O operator based on the admissible permutations in the sense of the following reference. Also, a restriction that has this definition is that the set of all admissible permutations with respect to the partial to all the admissible permutations can be very wide. We propose in the paper where we have presented a third approach, but here I don't have time, so I am going to present just these two definitions. And now I'm going to pass to the application. So, as I have said you before, we are going to apply this kind of multi-valued induced operators in order to fuse multi-valued time series predictions or predictors, predictions that come for a different number of models. In this case, we are going to take into account the P as number of models, the T, the number of time steps that they are in the time series. So for each P and each T, we obtain a multi-valued prediction in this way. The models that I have used, they are kernel-rich regressor, also two bagging and boosting regressors, and two recurrent deep learning models, long short-term memory and gated recurrent unit. Once that we have the prediction, we calculate the accuracy with respect to the truth value. We have used the following metric for accuracy because it's a simple metric based on the mean absolute percentage error. It's also a simple metric which is bounded in 0, 1 for each value. Once that we have the predictions and the accuracy, we calculate the set of admissible permutations. In science, for sake of simplicity, we have used the first case, the case of the set of admissible permutation based on the admissible order. So we want to order the best, the predictions based on the best ones, no? Taking into account a total order. So once that we have also calculated the best admissible permutations, we need to calculate the weighting vector for the vector-induced OA. In this sense, we calculate the weighting vector in a simple way, taking into account the minimization problem with an error function and with the restrictions of the IO operator, and we calculate with linear programming method. Okay, so once that we have the set of admissible permutations, the vector, the within vector, and the predictions, we can obtain the predicted aggregated value by means of the vector-induced O operator. This is more or less the methodology that we have used in the process. We have used the following data sets. There are data sets, they are multi-valued time series data sets from 3, 4, and 5 variables. Almost all of them are about economic data. Here you have some information in the footnote. The functions that we have used in the problem or in the applications are the following: are 5 vector-induced OAS constructed by means of admissible orders, and these admissible orders constructed by means of the following functions. Note that in the case that we have less than 5 dimensions in the multivariate time series, we take the first position of the sequence of the construction of the admissible order. And also we have compared with the arithmetic mean with the last time best prediction, and also with the arithmetic mean between the last and the best second predictions. Here we have some numerical results taking into account or evaluated with the mean absolute percentage error. We have used also another metrics, but I prefer to present the mean absolute percentage error because I think that is easier to interpret. As you can see here, the best results, at least numerically, are obtained when we use bio operators, and concretely bio with sequence 4 and sequence 3. And also to show more graphically, we can see here, this is the difference, the difference each other. We can see that the difference between S2, S3, S4, and S5 is minimum, it's very near to 0. But if we compare their aggregated results with arithmetic mean or the other function that we have comparing with, the percentage or the mean percentage is greater. Okay, so finally, as you have seen, we have presented a novel approach about vector aggregation. Also, we have presented at least a small demonstration about the effectiveness of these operators in the context of vector value predictions. On the future lines, we would like to relate these vector induced operators with interval valued induced operators, where we can measure, we can represent somehow the uncertainty with these intervals, and also this connection opens avenues for applying these techniques to fuzzy time series where the modeling of the uncertainty can be crucial. So thank you very much. Maybe you have any question.
Minutes for questions. Okay, maybe my small reaction. I like very much the idea how to rewrite the standard Iowa operator, because in the standard case, you have to apply arithmetic mean for all the possible sums, where you consider some specific z, which reorders the input vector. We played little time with the possibility to extend or to describe this situation using some, let's call it, chain-based integrals, because the chain is behind everything, and how to move change. And I like the idea or the trick you used, that you do not need any permutation because you consider all the possible admissible. So I like it very much. So just the comment that may be some possibility to extend it to some, again, my passion, integrals, because there exists induced Choquet integral, and this idea is very nice for me. So I have to go deep in this idea and to look the details and think about it.
Okay. Thank you very much, Andre, for the question. Um, we have thought, because as you know, we are familiar with socket integrals and in general fast integrals. The main motivation was the idea of having some induced vector aggregator, and IO operator, it was the most simple one. Of course, I think that the idea of extending or generalizing in sense of integral is a good idea. I am not very familiar with the issue of chains, but I think that is a very is a current future line for this work.
Other suggestions for cooperation, questions, remarks? If not, thanks the speaker again.
Yes.
Yeah, we are perfectly on time. So we will continue with the next Spanish contribution, this time presented by Alfonso Indurain Ibero. So the stage is yours.
So thank you very much for the introduction. My name is Alfonso Indurain Ibero. I'm a PhD student from Pamplona in Spain. And today I'm going to introduce you a new aggregation function designed explicitly to work with datasets that do not follow normal distributions. This work has been done in collaboration with Professor Pedregal from the University of Rio Grande do Norte of Brazil, my PhD advisors, Miquel Ferrero and Javier Fernandez, and Professor Bustince from the Public University of Navarre. So my intention was to start talking about the foundations of our work, which are OWA and induced OWA operators, but as the previous talk has already done so, I will just keep the definitions and go ahead with the proposal. So instead, I'm going to start talking about the past. What has been done about OWASP? What has been done about IOWASP? So what is the state of the art? To do so, we started researching the state of the art, and we started making this table, summing up some of the most important contributions of both OWA and IOWA. And then we started looking to see if there's some gaps or some places that we could find somewhere to work on. We realized that there were two main areas that have a little bit of work to be done. And the first one is related to the weight constraints. As you can see, most of the contributions keep the weight constraints to add up to 1. And there has been some works like the non-monotonic OWASP by Jagger that try to change these conditions and allow them to be greater than 1. So the question left is, why cannot they be lower than 1? So that is one question that can remain to be answered. But the second one, and the one that is most important to us, is that we haven't seen any study that any study that studies the effect of assuming that the distributions of the datasets are not going to be influencing the results of either OWA or IOWA operators. The reasoning for this is that OWA and IOWA operators, as has previously been said, depend on weighting vectors. And these weighting vectors usually can be obtained in several ways, but two of the main ways that they can be obtained are using weighting functions or maybe just simple optimization methods. And it is that second option that we are very interested in, because optimization methods relies usually on minimizing functions or linear programming. And these kind of methods rely heavily on the distribution of the data sets, because the output assumes the same, is going to be the same distribution as the inputs. But in reality, usually that is not the case. Data sets are usually heavily skewed, and assuming this kind of distributions can heavily influence the output of these weighting minimization processes. So the question remains, should we change the optimization methods, or should we design a new aggregation function that deals with these kinds of problems? So no surprise that we are from Pamplona, so we decided to work with the aggregation functions because otherwise I will not be a student of boosting. So in this presentation, I'm going to introduce a new version of the induced OWA aggregation function, which is going to be called restricted induced OWA operator. But before talking about the definition of the operator itself, I'm going to just try to justify the naming of the new operator. So restricted. The reason we decided to call it restricted is because we are going to limit the inputs of the aggregation. As I said, the distribution of the dataset is going to be heavily influencing the weights. And one of the reasons for that is the possible presence of duplicate data or the possible duplicated points on the datasets, which can heavily influence the outcome. So instead of allowing any kind of input into the aggregation, we are going to restrict only the input to be unique values. So if there are any duplicates in the input vector, we're going to remove it and just work with just one single example of them. So thus we are restricting the input of the operator. And then we could say, okay, we can work with OWA or we can work with the OWA. So why we are not going to give the boot to the induced characteristic? So why we are going to work with an induced OWA? The reason is that even though duplicated data can sometimes be helpful to the optimization methods, there is no doubt that duplicates appear for a reason. They have very relevant information that if we remove them completely, we will miss. So one possibility is to introduce this information rather than in the inputs itself, in the induced vector that is going to be used to sort the parameters of the induced OWA. And lastly, we have arrived to the definition. So for those of you who are familiar with induced operators, you can see that the definition is quite similar to the original one, but with a few small changes. The first one is the operators, the values that we are going to be using. The input is going to be a value vector x with any kind of inputs, but we are only going to work with x prime. X prime being just the unique values of x, meaning that we are going to remove any kind of duplicated numbers or values whatsoever. Second, we are going to sort it according to a segment permutation, similar to the original OWA, but this permutation is going to always be dependent on the number of duplicates, meaning that if, for example, an input, let's say x1 is repeated 3 times, its inducing vector is going to be the number 3, okay? And lastly, we are going to multiply it by a vector w, which is a weighting vector. However, as we are going to remove values from the input, we decided that maybe it's not the best idea to keep a normal weighting vector, but rather than work with what we have defined as a sub-weighting vector. A sub-weighting vector is a set of weights that, rather than adding up to 1, they can be allowed to be lower or equal than 1. Thus allowing for some kind of uncertainty related to the removed elements from the original input. One problem that we found during the development of this operator is that when we work with normal operators, we just need to create to obtain one single vector, which can be applied to any row of our dataset. So if we have a dataset with 4 columns, we just need a 4 weighting vector. But if we start removing elements, we cannot just work with one vector because we cannot apply a vector of 4 elements, for example, to this row because only we have 3. So instead of that, we are going to work with several weighting vectors. So we are going to select a new weighting vector for its possible length on our dataset. And fun fact about this approach, we later discovered that it is computationally faster and cheaper to achieve to optimize the weighting vectors in this way rather than optimizing just one single vector for the whole datasets. So now that we are done with the definition, let's talk about something that both theoretical and applied researchers have in common. But if you haven't noticed, I'm an applied one, so I will be much happier talking about this. So datasets. We all want the datasets, yeah? We want to prove our theories, to prove our methods, and for that we need datasets. But we don't want any kind of dataset. We want some kind of characteristics from dataset. So, for example, if I were to ask you what would you expect from a dataset, someone will say diversity, others will say diversity, others will say maybe cleanliness, relevancy, and so on and so on. But if you were to ask me, I have just one requirement: is always complete. That is completeness. Okay, sets are assumed to be complete, but that's not the case. Usually, when we work with datasets, there are some kind of missing instances, maybe some of the classes, maybe some of the inputs. There will be always something missing. And we always assume that they are going to be complete, but that is not actually the case. And let me just put an example here. In this paper, the authors try to look for every survey and every questionnaire that they could find about, in this case, sociological studies. They try to they look into all the results, they look into all the questions, and they discover that nearly half of them have missing data. Okay, so missing data is something that is very common and is going to be always present whether you like it or not. But now the next question is it relevant or should we ignore it? Well, you can do as you please, really, but I will argue that ignoring missing data can go from just simple reduced data sets to most dramatic problems like the distortional statistical characteristics of the data. So I will argue that we cannot ignore them. So one possible solution is to try to work with missing data imputation or deletion problems. But we're going to focus on missing data imputation, which is not perfect, but at least will help us to improve the characteristics of the data sets and thus making the results be more reliable. So to test our contribution, we have implemented the OSMCI framework, which is a data imputation framework designed based on clusterings and basic imputation. So assume that we have a data set with several missing instances. Initially, those instances are imputed with using single imputation. So for example, the mean of all the column or the median or some single aggregation like that. Then the data set is divided into several sub-data sets using sub-selection or some kind of some kind of other methods for increasing the diversity of the data sets. Then clustering methods are applied to each of these data sets and further refined into just trying to go back into the original missing data and saying, okay, I originally inputted the data with, for example, the mean, but obviously the mean is not going to usually be a very good or reliable method value. So we are going to try to refine it. By doing the several clusterings, we can arrive to several points that are close to the one that I'm trying to recover. So given these points, the original authors decided to aggregate them using the OWA and the OWA operator. So that is why, for us, it is perfect that at this point we are going to try to work instead of OWA with the restricted OWA operator and compare the results with the ones obtained in the original article. So here are some of the numerical results that we have obtained. But before talking about them, just to clarify them, all of these 6 data sets that we have been working with are heavily skewed. So they are not normally distributed so that we can prove whether or not the removal of the duplicated data that the restricted OWA performs is or not suitable for normally distributed data sets. So just a quick explanation of this graph. You can see here that any marker in gray is going to be representing the restricted OWA operator. Any marker in red is going to be the IOWA, and any marker in blue is going to be the OWA operator. This, the shape of the marker is just whether we have started the initial imputation with the mean, the mode, or the median. And another remark is that we are displaying errors, not accuracy. So the lower the marker, the better for us. So if you can see, in most of the time, in 5 out of the 6 data sets, our restricted IOWA operator is going to be outperforming both the OWA and the EOWA, except in this one, which actually is the only normally distributed data set that we have checked. Another test that we have performed is, okay, we have been designing a new aggregation, but is it dependent on the initialization of the weights, or is it really the optimization method that is going to take the price home? to check that, we repeat the experimentation with up to, I think, 30 or more different initialization of the weights. And we said, okay, if the weights tend to end up being similarly, then the variance should be close to zero. And thus the optimization method is not dependent on the initialization of the weights. And that is what we have been seeing here. And is that in every point of the data set, most of the weights variance are close to zero, meaning that the optimization method is always achieving the same results, meaning that the initialization of the weights are rarely at all relevant. Just in 2 of the 30 cases were relevant. So to sum it up, in this presentation, we have defined a new aggregation function designed to work especially with undistributed data sets. We have proven with several tests that assuming that replacing or removing the duplicated data from the input of the aggregation can be beneficial in cases where the data sets are skewed, and there's just one question to remain in what we're going to do next. And the question is, the answer to this is that we just want to answer one question. Is the restricted EOA necessarily to be an EOA, or can we just try to work with a restricted OA operator and get rid of the induced characteristics? Thank you very much for your attention.
Thank you, Alfonso. We've got quite a lot of time for questions and remarks. Okay, I'm a theoretician, so I'm interested in the restriction procedure because, as far as I understand, if you have a vector, you somehow you have some induced vector. So maybe the other question will be what's the role of the induced vector in this whole study. But first of all, if I replace or remove the dimension of the vector, then of course some problems appear. For example, you have to compute or to generate new weights or how to obtain them, because if you reduce the dimensionality, whether the normality is useful or not, whether the sum of the weights should be always one, or how to do. And this resembles me one of our work related again with the chain-based integrals, because in the case of restriction, you do not have a maximal chain, because each ordering of the vector is in one-to-one correspondence with some maximal chain of the sets from the basic set. And if you remove something or destroy something, then you get something smaller, need not be maximal. And of course, again, my part, Choquet integral and integrals in general, and they are related somehow with maximal chains. And what about to consider something non-maximal, what we obtain? And one of the result was that we are able to cover Iowa approach using the non-maximal chains. So it was written in one or two papers regarding maximal chains, Choquet integrals. So maybe the question is, what's the first question? What's the role of the inducing variable in your study? Because I did not see any mentioning inducing variables in the beginning.
Yeah. So the role of the inducing variable is that whether we like it or not, the duplicated data holds very important information because they are duplicated for a reason. Yeah. In the case of, for example, of clusterings, if you have multiple duplicated data, usually means that you have several clusterings, and they all are saying that this value is important for a reason because we always end up with this value after the clustering. So we discovered through experimentation that, as I said, duplicated can affect the optimization methods, but also that they are very important, as I said. So we decided to introduce that the information relevant to the duplications into the induce by saying, okay, if our clusterings are saying that this value should be the result of the clusterings are 3 times, for example, the induce is going to be 3 times, so that then the inputs are sorted according to that, the amount of times a value is duplicated. So the optimization method should prioritize, as they usually does, the first elements and then the second ones and so on. So for example, if I have like 5 clusters that said that the value should be imputed using x1, then x1 should have an inducing vector of 4, then thus it should be one of the first elements that enters the aggregation when sorting.
Yeah, I can see it now. Thanks. Some other questions, remarks? Everything is clear. Perfect audience. So, okay, we are on time, so thank the speaker again. And we will finish this session. Yeah, I've got the deja vu. But now I'm not going to introduce myself. I'm going to introduce my PhD student finishing this year, where the big project of PhD dissertation is related or inspired by music. So that we have a small part of this result. So Kristina Urajová from Košice.
Good morning, my name is Kristina Horajová, and I will be talking about aggregation operators and algebras for musical data fusion. First, let's think about how music actually works. Music isn't static. The chords are formed gradually, tones enter over time, and instruments join one by one. When we hear a final sound, we don't care in which orders were added or how were they grouped. For example, we don't care in which order, we don't care how we combine if we combine firstly strings and then add winds, or if we mix everything together. It immediately leads into two mathematical requirements, associativity and commutativity. At the time, perception doesn't operate on physical scale. Pitch and loudness are perceived non-linearly. So if we want to aggregate a musical sound properly, we need to aggregate on a perceptual scale. And this is the point where the aggregation operators enter the picture, and naturally leads us to PIF framework. Aggregation functions are used in many areas, such as information fusion or fuzzy logic. And the common framework is given by extended aggregation functions, but this framework is very weak when associativity missing. The result may depend on order or grouping, and it may be a serious issue in the aggregation sound. A simple example is arithmetic mean, because for 3 different values, a different grouping may give different results. And moreover, perception suggests that higher arithmetic potency isn't natural, because several identical instruments playing together don't sound like a single one. And to aggregate musical sound properly, we need operators that behaves consistently when applied repeatedly. And this leads us to binary, commutative and associative binary operators that can be iterated independently on a number of inputs. And these operators we will call iterative form preserving aggregation operators, shortly PIF operator. And key idea is that the same algebraic structure is preserved for all arities, and each PIF operator is determined by its binary generator. This example shows that PIF operators include several associative operators such as addition, multiplication, minimum, or maximum. These operators are commutative, associative, and incremental, and adding one element doesn't change the rule. The interesting example is a parallel or a harmonic sum, because it doesn't depend on, or it doesn't use a normalization factor depending on number of inputs. In contrast, they exclude mean-like operators, arithmetic, geometric, harmonic mean, because they depend on number of inputs. When the PIF structure is fixed, many properties follows automatically. The aggregation is invariant under permutation and grouping. It's monotone. It behaves consistently with neutral and absorbing element, and aggregation of those give 0, and all ones give 1. So now we see how to construct new PIF operators from existing ones. The first construction is based on algebraic duality for unit interval, and fixed constant. It corresponds to De Morgan duality for T norms and P conorms. And in the second example, the second construction, or in the second construction, is important closure and monotonicity, as we follow in next counter examples. This counter example show why closure is essential, even if base operator is associative. It may produce values outside the admissible set a single step, and once it's happened, iteration is no more longer possible, and associativity cannot be formulated. And in the second counter example, we show why monotonicity or the inverse is essential, even if base operator is well behaved and G is isotone. Choosing non-monotone right pseudo inverse may destroy isotonicity. Now, natural question is if PIF operators are stable under composition, and pointwise composition seems intuitive. We aggregate firstly in parallel and then combine the results. But associativity seems to be very fragile, because even if all operators are associative, the composition may fail to be, as we can see in this example. So additional compatibility properties are needed, but these properties may be very restrictive. So this motivates to search for weaker and more interpretable assumptions, which we show in this proposition. In this example, we show we combine linear and nonlinear, linear superposition and nonlinear interaction term, and this composition relies with this necessary condition. And the key idea is that silence acts as a neutral element, and when one input is 0, then the nonlinear interaction term disappears, And this means that this construction is both physically and perceptually meaningful. And musically, this means that when we add instrument which plays quietly, nothing will change. Besides the pointwise composition, we look at the context-dependent composition. In this construction, the aggregation of one input depend on the another as well. In general, this construction doesn't preserve the PIF property, but this proposition show a simple sufficient conditions under which it does. In many cases, this construction collapses into simpler operator. In the first two cases, interaction has no has no effect, and in a second, in third case, it is reduced to a simpler binary operator. Context-dependent composition seems to be very restrictive. Under the natural sorry. Selector assumptions, sorry, under the natural selector assumptions, associativity forced a strong algebraic structure. One branch of this composition must be an endomorphism. And many of associative operators don't satisfy it when we combine them. If we can see in this example that even common operators such as probabilistic sum doesn't satisfy these conditions. And this theorem shows that Zadek extensions into a more general framework, PIF framework. The key idea is aggregation into levels. Locally, we aggregate membership degrees, and then global, we aggregate all local contributions. When these two operators in two levels are compatible, the resulting operator is associative, commutative, and monotone. And this shows that associativity doesn't depend on supremum or specific T-norm, but it follows from endomorphic interaction between two levels of aggregation. And this example shows that PIF framework acts exactly as we expect. This means that adding some voice doesn't change perception result. Now we fix algebraic structure to aggregate tones. We consider tones as primitive objects and associated with pitch values in ordered set, ordered space. Pitches aren't aggregated directly, but via via a perceptual transformation, and intensities acts as weights and are combined additionally. A basic requirements is still that aggregation doesn't depend on the order or grouping, and the first theorem shows that our operation has this property is it's associative and commutative, and the second theorem shows that it's very restrictive, and when we want a natural algebraic structure, the weights must be barycentric, and musically it means that if a tone have if louder tones have a more effect, and aggregation is incremental, that there is only one possible construction, and this construction looks like this. And finally, this example shows that the choosing generators fixes aggregation scale. Logarithmic aggregation leads to weighted geometric mean, and it fits into Weber-Fechner law and pitch perception. Using identity leads into weighted arithmetic mean, and it corresponds to linear physical superposition, and choosing inverse generator leads to weighted harmonic mean, and it's used in acoustic and harmonic relations. It's everything, and thank you for your attention.
Thank you very much. So we've got time for questions and remarks. It is strange for me to ask myself or Christina, so I will be quiet for a time.
Okay, maybe it will be childish. So if I understood, it was like one part was somehow covering the music from the frequencies part as a sounds, and then from interval part. No, there were some these groups and so it was like and how you classify if such intervals are in some harmonic consonant way or something? Or
what do you mean by interval? Because
intervals between tones, between sounds. Or no, you don't manage that.
It should be explained that the basic idea is that
Can you go back or like 5 slides?
If you are in concert and you have a teacher and
no, one more.
And a student, and they're playing together, and if the teacher plays much more louder than the student, the resulting sound is pleasant. But if it is vice versa, that the student plays very bad and teacher plays
so
in a smaller intensity, then the resulting sound is not so pleasant. So how to aggregate the information, which depends on two variables. It means on pitch and intensity.
Okay.
How to aggregate them together. And the result is interesting for me, at least, because in the standard case, if you have arithmetic geometric harmonic mean, they are not associative at all. But if you combine in a clever way the information from pitch and intensity, then you obtain commutative and associative operator, which is very nice thing. And the one of the results said that it is the only possibility how to, in this setting, you can do it.
So your view is like that two players plays almost the same thing, but one better than another, and what will be the result. So my view is like that two players plays something different, but in a harmonic way. How to somehow, because I saw this slide about intervals, and so I think that you mentioned this. Okay.
So
Okay, thank you. I think we will continue speaking about that.
Sure. Because it is like multiplication of complex numbers. If you do it coordinate wisely, it's a stupidity because it does not have properties you expect. So you have to combine, you have to do some mixture of intensity and pitch together, and this is the resulting operator somehow here. Yeah. So if you just add two intensities, let's say in logarithmic scale, then you have to combine all the information in the first coordinate, pitch as well as intensity. And how to do it, this is a possibility, and the next theorem says that it is the only possibility if you want to have commutativity and associativity.
Okay, thank you.
Further questions, remarks? If not, to thank the speaker again. Thanks all the speakers again, and thank you for participating on this session, and enjoy your meal.